My name is Dennis Morris. I'm a mathematician and theoretical physicist. In this series of videos I'm showing you the results of 20 years of research done by myself into the nature of empty space. This is the fourth in this series of videos upon the nature of empty space. In previous videos we have seen that if we are given a finite group, we can get a rotation matrix replete with a set of trigonometric functions and a distance function directly from that group. In fact, we can get several sets of these distance functions and rotation matrices. We call a set of such objects a rotation matrix with its trigonometric functions and the distance function a finite group space. There's a little more to this than we've let on before. Each of these finite group spaces is a type of number. We're now going to delve into the nature of numbers. You will recall that we derived two-dimensional Euclidean space from the 2 by 2 representation of the order 4 finite cyclic group C4. We actually have the polar form of the two-dimensional complex numbers here. But let us look more closely. We need to consider the multiplication operation within the complex numbers. When we were younger, we were told that complex number multiplication is something to do with the square root of -1. Looking at the multiplication operation of the complex numbers, we see that it seems weird. Why do we not simply multiply the two real parts together and multiply the two imaginary parts together? Where does this weird multiplication operation come from? This weird multiplication operation is really just matrix multiplication. We also see where the square root of -1 fits in. Great. Now we understand why the complex numbers have such a weird multiplication operation. But hang on a moment. All the complex numbers really are is beefed up permutation matrices. Matrix multiplication of beefed up permutation matrices is really just a combination of permutations. What we're really doing when we multiply complex numbers together is we're sequentially combining permutations within the group C4. The four basic elements of the complex numbers correspond to the four permutation matrices. When we multiply two complex numbers together, we are really multiplying permutation matrices together. We are really sequentially combining permutations. We are really working within a finite group. In this case, the finite group is C4. What is addition? Addition is adding different amounts of the same permutation together to produce an amount of the same permutation. What is multiplication? Multiplication is sequentially combining together two permutations to form a third permutation. In what ways can we combine two permutations together to make another permutation? Well, we can add different amounts of the same permutation together to produce another different amount of that same permutation. We can also sequentially combine permutations together to produce a third permutation. We see that at a fundamental level, addition within the complex numbers is adding together two permutation matrices of the same type. We see that at a fundamental level, multiplication within the complex numbers is the sequential combination of two permutations together to produce a third permutation. This is general throughout all types of complex number. When I was at school, I used to think that multiplication was no more than successive addition, that multiplication was no different from addition, just done lots of times. That's true within the one-dimensional real numbers, because the one-dimensional real numbers are based on only one single permutation, the identity permutation, the order 1 finite group. When we come to the complex numbers, things are very different. Multiplication is sequential combination of permutations. Addition is adding the same permutation to itself. I want to really drive this home. Addition in all number systems is nothing more than adding the same permutation to itself. Multiplication in all number systems is the sequential combination of permutations. Both of these operations produce another permutation. Furthermore, they produce a permutation within the same finite group. Since multiplication is sequential combination of permutations, and the sequential combination of permutations is not always commutative, multiplication is not always commutative. Now, multiplication within the complex numbers is always commutative because the four permutation matrices that underlie the complex numbers are the finite group C4, which is a commutative group. But when we come to the quaternions, we'll find the permutation matrices which underlie the quaternions are not commutative, and therefore multiplication within the quaternions is not commutative. Since addition is adding the same permutation to itself, addition is always commutative. On the face of it, the two ways of combining permutations together and getting another permutation, which we call addition and multiplication, are the only two ways to combine two permutations together and get another permutation. Thus there are two algebraic operations. There's the addition algebraic operation, combining a permutation with itself, and the multiplication algebraic operation, sequentially combining two permutations together to give another permutation. This is the standard mantra of abstract algebra. There are only two algebraic operations, addition and multiplication. However, it is wrong. In some finite groups there is a third way of combining two permutations together and getting a permutation. This third way is called the commutator. This is a third algebraic operation. It occurs only in some finite groups. So what is the complex plane that we call two-dimensional Euclidean space? It is two pairs of directionally opposite permutations. The four permutations together are the group C4. That's the complex plane. That's a kind of two-dimensional number. We normally label the axes of the complex plane with +1, -1, +i and -i. But we could equally well label the axes of the complex plane with the four corresponding permutations that are the order 4 cyclic finite group C4. We see that the two-dimensional complex plane is really a space of four permutations. The axes of the complex plane are permutations. So, why are the axes of the two-dimensional complex plane at right angles to each other? The axes of two-dimensional space-time are not at right angles to each other, but the axes of two-dimensional space-time are independent of each other, just as are the axes of two-dimensional complex numbers. Each axis is a permutation. You never get permutations mixed together. They are all independent of each other. That's why the axes of a space are independent of each other. I don't use the word orthogonal because there are so many connotations to it. The axes are independent because each permutation is independent. So why are the axes of two-dimensional Euclidean complex numbers at right angles to each other? The right angle is in the trigonometric functions of the Euclidean space. The trigonometric functions of two-dimensional space-time do not contain right angles, so the time and space axis are not at right angles to each other. But they are independent because they're both permutations. And yet again, why are there two algebraic operations in the complex numbers, addition and multiplication? Because there are two ways to combine commutative permutations together and get a permutation. There's three ways to combine non-commutative permutations together and get a permutation in some cases. I have used the two-dimensional Euclidean complex numbers to demonstrate the fact that numbers are really just permutations. They're permutations within a particular finite group. As we continue with this video, we will meet higher forms of complex numbers, three-dimensional forms of complex numbers, four-dimensional forms of complex numbers. Each of these types of complex number is a finite group space. Finite group space, rotation matrix, distance function, trigonometric functions, etc. Type of complex number. In each case, this type of complex number is basically a finite group of permutations, and the finite group space has axes which are basically just permutations. It's all rather simple really, isn't it? There is a point I need to clarify. What is a division algebra? If you ask a mathematician this question, she will tell you that a division algebra is just a kind of numbers, and she might give the three known examples of the real numbers, the two-dimensional Euclidean complex numbers, and the quaternions. If you seek more detail, she will tell you that any set of mathematical objects which satisfy the 13 division algebra axioms is a division algebra, and she will list those 13 division algebra axioms. The division algebra axioms are things like associativity, multiplicative closure, multiplicative inverses, additive inverses, a multiplicative identity, and absence of zero divisors. If you ask the mathematician where these 13 axioms come from, she might say something about them being cast down by a great spirit in the sky, written in stone, and there might be a burning bush in there somewhere. However, if you do not accept this, she will admit that the mathematicians just copied the division algebra axioms from the real numbers. They looked at the real numbers, the two-dimensional Euclidean complex numbers, and the quaternions, and they wrote the division algebra axioms as observed properties of these established types of numbers. No burning bushes anywhere. Two of the division algebra axioms are additive inverses, that's negative numbers, and an additive identity, that's zero. We have the two-dimensional hyperbolic complex numbers. The two-dimensional hyperbolic complex plane is two-dimensional space-time. The hyperbolic complex numbers satisfy all the division algebra axioms except two. There are no additive inverses on the real axis. E to the power of a can never be negative, and there is no additive identity. E to the power of a can never be zero. It seems to me that the concept of division algebra ought to include the hyperbolic complex numbers and other group space kinds of numbers like the hyperbolic complex numbers. This means the axioms need to be amended so that they do not insist on additive inverses on the real axis, and that they do not insist on an additive identity on the real axis. If we do this, every finite group space becomes a type of division algebra. Reality seems to agree with me. We do see two-dimensional space-time in reality. Reframing the concept of division algebra to include the hyperbolic complex numbers means that we go from having just the real numbers, the two-dimensional complex numbers and the quaternions to a situation where we've got types of number of all dimensions and an infinite number of them. Every finite group space becomes a division algebra. We are taking the view that a finite group space is a type of numbers. The axes of that finite group space are just permutations of a finite group. The axes of that finite group space are independent because permutations are all independent. We are taking the view there are two algebraic operations within a commutative finite group space because there are only two ways to combine two permutations together and make another permutation. The first of these algebraic operations is addition, where we simply add two different amounts of the same permutation matrix, producing more of the same permutation matrix. The second of these operations is multiplication. Multiplication is the sequential combination of permutations to produce a third permutation. That's why there are two, and only two, algebraic operations within a commutative finite group space. As we mentioned earlier, in some non-commutative finite group spaces there is a third algebraic operation which we call the commutator. How do we differentiate within the two-dimensional Euclidean complex numbers? You will be aware of the Cauchy-Riemann equations. We're going to differentiate in a more general sense. We have the basic differential separated into four parts. We can rewrite this. We now have the differential written as four real differentials. Doing the calculation gives the divergence and the curl of the function we differentiated. If we differentiated a real function, we would get the gradient. Clearly, the complex function is acting as a potential. An important point is that the curl appears in the part of the matrix associated with rotation, the imaginary part. Functions that satisfy the Cauchy-Riemann equations are included within this general form of differentiation. We have seen the two-dimensional Euclidean curl and the two-dimensional Euclidean divergence emerge from the two-dimensional Euclidean complex numbers. Each finite group space has its own type of curl, its own type of divergence. We have the divergence and the curl of two-dimensional space-time. Notice the signs. These should be in the same one matrix, but we have separated them for clarity of exposition. We have the divergence and two curls of our three-dimensional space. We have seen that each type of finite group space has its own type of curl and its own type of divergence. Thus, a finite group space is not only a distance function, a rotation matrix, and a set of trigonometric functions, it is also a curl and a divergence, and actually also a Laplacian as well. The two-dimensional Euclidean space of the complex numbers has a two-dimensional curl, Euclidean curl. The two-dimensional space-time has a two-dimensional space-time curl. Our four-dimensional space-time can accommodate both the two-dimensional Euclidean curl and the two-dimensional space-time curl because it is a multi-rotation space that can support both two-dimensional Euclidean rotation and two-dimensional space-time rotation. There are very few finite groups which have a curl that would fit into our four-dimensional space-time. Those very few finite groups give an exact match for the Fermion content of the universe. A Euclidean curl is a rotation sort of thing, what we're used to, what we call rotation. An example of such a Euclidean curl in our space-time is the magnetic field. A space-time curl is to do with space-time rotation. Space-time rotation is change of velocity. An example of a space-time curl in our space-time is the electric field. In the electric field, a charge is accelerated by the electric field. That's a space-time curl. We've now come to the end of this fourth video in our series of videos about the nature of empty space. The next video, which is the last video, the fifth video, is the video where we will actually deduce our four-dimensional space-time as a superposition space. I hope you will not be offended if I use the next few seconds to advertise a few of my books. Thank you very much for your attention.